on the topic of joint probability distribution. If you have two discrete random variables like x sub 1 and x sub 2, so here we have a discrete random variable x1 and the other one is x2. We write the probability that x1 will take the value x1 and x2 will take the value x2 as probability that x1 is x1 and x2 is x2. Consequently, the probability that x1 takes on x1 and x2 takes on x2 is the probability of the intersection of the events x1 is x1 and x2, random variable x2, takes on x2. We refer to the function f of x1 and x2, which is the probability that x1 is x1 and x2 is x2, and the corresponding possible values of x1 and x2 as the joint probability distribution of these two discrete random variables. In general, for discrete random variables, the probability that x1 and x2 belongs to set A is the double summation of P of x and y such that x and y belongs to set A. So basically, you need to add the values together. Let's go over one example together to feel comfortable about this topic. Let x1 and x2 have the joint probability distribution in the table below. Joint probability distribution of f of x1 and x2 of two random variables x1 and x2 is given below. Note that x1 and x2 both are discrete variables. x1 can take on 0, x1 can take on 1, and x1 can take on 2. x2, on the other hand, can take on 0 and 1. Well, in this example, the probability that x1 is 0, x2 is 0 is 10%. The probability that x1 is 1, x2 is 0 is 40%. The probability that x1 is 2, x2 is 0 is 10%. And the probability that x1 is 0, x2 is 1 is 20%. The probability that x1 is 1 and x2 is 1 is 20%. And finally, the probability that x1 is 2 and x2 is 1 is 0. Now the question says, calculate the probability that the summation of these two variables is more than 1. By eyeballing, if you take x1 to be 1 and x2 to be 1, 1 plus 1 is 2, which is more than 1. x1 can be 2, x2 can be 0. The summation is still more than 1. x1 can be 2, x2 can be 1. 2 plus 1 is 3. So it seems like we have 3 probabilities to add. The event x1 plus x2 more than 1 is composed of the pairs of values 1 and 1, because 1 plus 1 is more than 1. 2 and 0, 2 plus 0 is more than 1. And finally, 2 and 1. 2 plus 1 is 3, which is more than 1. Now, the probability that x1 plus x2 is more than 1 is f of 1 and 1 plus f of 2 and 0 plus f of 2 and 1. F of 1 and 1 based on the table is 20%. F of 2 and 0 based on the table is 10%, and f of 2 and 1 based on the table is 0. So if we add all of these together, it is going to be equal to 30%. Now I expect you to ask, what if we have continuous random variables? What should we do then? Let x and y be continuous random variables. A joint probability density function, f of x and y, for these two variables is a function satisfying the function must be more than or equal to 0, and the double integral, iterated integral of f of x and y dx dy as x and y ranges between -infinity to infinity is equal to 100% or 1. Then, for any two-dimensional set A, the probability that x and y belongs to that set is the iterated integral over the set A of function f dx dy or dy dx depending on the area that you're dealing with. In particular, if A is a two-dimensional rectangle, which is defined as the set of all x and y's such that x is bounded between two vertical lines and y is bounded between two horizontal lines, is the probability that x and y belongs to set A, which is in nicer form written as the probability that x is bounded between A and B and y bounded between C and D is the double integral of f of x and y with respect to y first, then the outer integral with respect to x, and you can switch these around by Fubini's theorem as well. Okay, let us take a look at one example. A bank operates both a drive-up facility and a walk-up window. On a randomly selected day, let x be the proportion of time that the drive-up facility is in use. At least one customer is being served or waiting to be served. And y, the second variable, is the proportion of time that the walk-up window is in use. Then, the set of possible values for x and y is the rectangle D, which is the set of all x and y's such that x is bounded between 0 and 1, y is bounded between 0 and 1. Suppose that the joint probability density function of x and y is given to us as f of x and y. As long as you are in that rectangle, it is 6/5 x plus y squared, otherwise it is 0. Question says, find the probability that neither facility is busy more than 1/4 of the time. Well, since we have joint probability distribution, and these are continuous random values, we're going to use iterated integral. So the probability that x is bounded between 0 and the 4th and y is bounded between 0 and the 4th is, you're going to write down the function 6/5 x plus y squared. You can take the inner integral with respect to x, then take the outer integral with respect to y, or switch around. It doesn't matter. Fubini's theorem says, since you have fixed boundaries, you can switch x and y. Just be careful about the order. In our calculation, we are using elementary integral methods. You can distribute 6/5 into parentheses and separate these two integrals. The inner integral for the first integral is the integral of x dx as x ranges between 0 and the 4th. And the number, the coefficient 6/5 can be written outside the integral. The outer integral is with respect to y. To calculate this, we're going to use the integral of u to the n du, which is u to n plus 1 divided by n plus 1 plus constant of integration. But please note that since you have definite integral, C disappear. Well, the inner integral is the integral of x dx, which is x squared divided by 2. X ranges between 0 and a fourth. And outside of it, you have 6 divided by 20. Why 6 divided by 20? Because the integral of 0 to 1/4 of dy is 1/4. The second integral is y squared, integral 0 to 1/4 of dy. So what I did, I just switched these two around for the second integral, so I can take the integral with respect to y, and I wrote down 6/5 outside. So this is y to the third divided by 3 of the integral of y squared dy. And as you saw before, the integral of 0 to 1/4 of dx is 1/4. 1/4 times 6/5 is 6 divided by 20. Now this is equal to 7/640, which is about 0.0109. So it's about 1.1%. That's how you calculate the joint probability distribution for continuous random variable.